Chapter 1 in your text begins by talking about functions in a very general sense. We're talking about sets of numbers, we're talking about whether something is a function, we're talking about notation, we're talking about finding the function of a number, and we're talking about piecewise functions. Okay, so hopefully you remember these sets of numbers that you were taught in Algebra 1. Natural numbers, the first counting numbers you ever learned. Whole numbers, which is natural numbers plus 0. Integers, which are those numbers and their opposites. So now we're bringing negatives in. And then rationals and irrationals. Rationals are anything that can be written as a fraction, and irrationals cannot. And then everything is real numbers. So we need to know these sets of numbers in order to write sets of numbers using set builder notation. So notice how set builder notation looks on your screen. Notice how we read set builder notation. We're reading it as the set of numbers x such that x has these given properties and x is an element of this set of numbers. So let's practice writing some sets of numbers using set builder notation. So in part A, I see that my numbers are 1, 2, 3, 4, 5, and so on. So again, remember what set builder notation looks like. We start with the set brackets, x such that x is greater than or equal to 1. And then we have what set of numbers x is an element of, and x is an element of natural numbers. And that's it. Part A. Part B. I have a set of numbers x such that x is less than or equal to -3. I can use that inequality in order to create my set builder notation. And since there's no other restrictions on the value of x, well, that means x is an element of the real numbers. And then finally, part C, I want all the multiples of pi. So again, set builder notation, x such that x equals a number being multiplied by pi. And anytime you're building a set of numbers where it's described as multiples of another number, that n that you're using as your multiplier is an element of the integers, which is abbreviated by z. There's another way to notate sets of numbers, and it's called interval notation. And interval notation kind of brings into play what these values look like on the number line. So I think it would be valuable to us to talk about what these inequalities would look like on the number line before we write it in interval notation. So part A, if y is between -4 and -1, then if I've got these two numbers on the number line, -4 and -1, notice that this one is an or equal to at -4, whereas the -1 is not or equal to. And if y is between those values, then it's this stuff. So when you're writing a set of numbers in interval notation, what you're doing is indicating the start value and the end value. And if the start value is inclusive, we use a squared off bracket. So since my start value is -4, that's the first number I write down, and then a comma, my end value is -1, but it can't actually equal -1. It's not inclusive. It can't equal -1. So we notate that with a parentheses. And that's interval notation. For part B, if I have numbers that are greater than or equal to -3, again, think about this on the number line, I'd have -3, it's or equal to, and it's these values. So again, you start with your beginning value, which is -3. It is inclusive, so I put a square bracket on that, comma, my end value. Well, I don't actually have an end value because it goes on to infinity. So we notate that. And since infinity isn't an actual value, we put a parentheses anytime there's an infinity involved. Part C, I've got my number line with -2 and 9, and they are both open circles, and x can be greater than 9, or x can be less than -2. So when we're doing interval notation, remember, we're showing what would be shaded in on the number line. So the first thing that's shaded in on the number line going left to right is -infinity. I need some more space for this. So it's starting at -infinity. And then it goes to -2. And then there's a gap. And then I have 9 to positive infinity. And in order to notate that I've got these two groups of possible values for x, and I want to consider all of those, then I unite those two sets of numbers. That U indicates that it's a union of those two sets of numbers. Okay, so that's a brief introduction to interval notation. And you've done this before. You've looked at relations and identified whether they were functions. You may recall the vertical line test. The main thing that you want to remember about what it means for a function to be a function is that there's only one possible output for every input. So in part A, if my input value x is the area code and the output value y is a phone number in that area code, is every x area code linked with only one y phone number? And the answer is no. Chances are that the person sitting next to you in class tomorrow has the same area code as you, but doesn't necessarily have the same phone number as you. So part A is no. Part B, I look at my X column and I notice that there's 2 5s in it, which means if you look at the right-hand column, input of 5 has 2 possible outputs, 8 and 9. That means it is also not a function. In part C, what you might use to identify whether this is a function is the vertical line test, kind of taking a vertical line and dragging it across that graph. and looking for whether your vertical line crosses the graph in more than one place. And it does not. So that means this is a function. Every x input has only one y output. Take a moment and work through the your turn below. Here we're refreshing our memory on how to use function notation to find a function value. Remember once again from Algebra 1 and Algebra 2 that when you are trying to find the function of a value, you're taking that value and substituting it in for the variable. So for part A, f of 12 is 2 times 12 plus 3 over 12 squared minus 2 times 12 plus 1. And then we just clean this up. 2 times 12 is 24. 24 plus 3 is 27. In the denominator, we have 12 squared, which is 144. From that, I'm going to subtract 24, because that's what 2 times 12 is, and then add 1 to it, and I've got 121. And this fraction does not reduce, so that's the answer that I would want. Part B, same idea. This time, however, you're plugging in an expression for the variable. So the function of 6x is 2 times 6x plus 3 over the quantity 6x squared minus 2 times 6x plus 1. And then again, you're just simplifying things. 2 times 6x is 12x, and I can't combine that with 3, so in my numerator I have 12x plus 3. In the denominator, I'm once again not going to have any like terms to combine, but I can still simplify this. Quantity 6x squared is 36x squared, and then 2 times 6x gives me a minus 12x, and then plus 1. And this expression cannot be simplified, so that's the answer that I would want. Take a moment and work on the your turn below. You will notice on your screen, in the interest of making the answer something that you can click on, what you're clicking on is just what the correct denominator would be. In the last lesson where we were reviewing quadratic equations and quadratic graphs, we did talk about finding the domain of the function and the range of the function. Here we're just going to talk about the domain of the function, and the difference between what we're doing here and what we did in the last lesson where we were identifying domain is that in the last examples where we did domain, we had the graph, so we could look at something on the coordinate grid and decide what kind of x's we were allowed to have. Well, here all I have is the algebra. So you've got to remember a few things about what you're allowed to do algebraically, and more importantly, what you're not allowed to do. You're not allowed to divide by 0. You're not allowed to take the square root of a negative number. Okay, so those are a couple of things that we want to make sure that we're looking at in these functions. So in the part A function, notice that I've got stuff in the denominator. Well, the last thing I want is that stuff being 0. So for part A, I might set the equation x squared plus 7x plus 12. Actually, I don't want to call it an equation because I don't want that to equal 0. And in order to figure out what values cannot be part of our domain, we solve this quadratic just like we did in the last lesson. So we kind of lucked out at factors to x plus 4 and x plus 3 that can't equal 0. So that means either x cannot equal -4 or x cannot equal -3. So the domain of each function is set of all numbers x such that x cannot equal -4 or x cannot equal -3. Other than that, x is an element of all real numbers. For part B, I don't have a denominator, so I don't have to worry about dividing by 0, but I do have a square root, and as I mentioned earlier, you're not allowed to take the square root of a negative number. So I want to make sure that a squared minus 4 is greater than 0. So a squared needs to be greater than 4, and when I take the square root of both sides, I need to be very careful about what kind of numbers I can square and be greater than 4. A can be greater than 2, or A can be less than -2. So that's my domain, and because of the nature of this domain compared to the last one, and the last one, that should have been a bracket. But in this last one, I used set builder notation, whereas for part B, it might be clearer to indicate this domain as in interval notation. Okay, so my interval starts at -∞ to -2 and unites with +2 to +∞. And that's part B. In part C, I have a few things going on. I want to make sure that I'm not dividing by 0 so that 2x plus 6 can't equal 0. And I also want to make sure that I'm taking the square root of a positive number so that 2x plus 6 has to be a positive number, meaning it's got to be greater than 0. So if it's greater than 0, I'm already ensuring that it doesn't equal 0. Okay? So the math that I need to do is ensure that 2x plus 6 is greater than 0. And I subtract 6 from both sides, divide both sides by 2, and as long as x is greater than -3, I'm in good shape. I'm not dividing by 0, and I'm not trying to take the square root of a negative number. So for this one, either kind of notation would make sense, whether you're using set builder notation, whether you're using interval notation. So myself personally, I'm going to go for set builder notation. My domain is x's such that x is greater than -3 and x is an element of all real numbers. Finally, the last concept we're touching on in this lesson is piecewise functions. And what a piecewise function is the kind of taking a function and breaking it down into smaller pieces and different ways to calculate that function. Okay, so according to this function, if the value of t is between 0 and 15, then I would find the output by multiplying that t by 4. If my input is between 15 and 240, then my output is 60 all the time. And then finally, if my input is between 240 and 250 inclusive, then I have to do negative 6t plus 1500, excuse me, in order to calculate the output. Okay, so for part A, since my input 5 is between 0 and 15, the V of 5 is 4 times 5, which is 20. Part B, since 15 is this part of my piecewise function, because notice the or equal sign, I'm doing the same thing again. The V of 15 is going to equal 4 times 15, which is 60. Pause your video to work on the your turn below.